Today's problem is number of ways to arrive at destination, difficulty medium. You are given an undirected weighted graph with V vertices numbered from 0 to V minus 1 and E edges. E is not actually an input. V is an input. Edges represented in the input as a 2D array, where edges at I equals U sub I, V sub I, time sub I. There is an undirected edge between nodes U sub I and V sub I that takes time sub I minutes to reach. Okay, that's a little bit confusing because normally we refer to those things as weights. I mean, if you look at a weighted graph here, in fact, they refer to it as a weighted graph. We refer to those as weights, these numbers that you see on the edges. Now, those can represent distance or cost or time or, but we usually just we usually just say weight. So anyway, there may be some difference of terminology here, where if you see time or weight in this problem, it means the same thing. Your task is to return how many ways you can travel from node 0 to node V minus 1 in the shortest amount of time. All right. So looking at the first example here, we want to go from 0 to 3. Now we can go straight from 0 to 3. That is a distance of 5. Actually, I just noticed we're using distance in the algorithm as well. But okay, yeah, you can go from 0 to 5, or you can go from 0 to 1 to 3. That's also 5. If you're going to go all the way around to 2, that's going to be too far. This one, there's actually a number of ways to get from 0 to V minus 1, which would be 5. You can go straight to it. That's 7. If you go through 2, that's 8. That's too much. You can go from 0 to 2 to 3 to 5. That's 3. That's also 7. You can go from 0, 4, 5. That's 7. You can go 0, 4, 1, 5. That's 7. So there are a total of 4 ways to do that. Vertices will be between 1 and 200 inclusive. Edges, size. Let's see. Edges. Number of edges. Yeah, will be between V minus 1, which would be, and V times V minus 1 over 2. If you get more edges than that, I think you're going to have, anyway, U and V, the vertices, will be numbered between 0 and V minus 1. Time will be between 1 and 10 to the 5th, 100,000. And U sub I will not be equal to V sub I. So no self loops. Time complexity V plus E log E, auxiliary space V plus E. All right, topic tags. Graph shortest path. All right. There's an algorithm called Dijkstra's algorithm that is commonly used to find single source shortest paths in a graph. It's not going to work quite. It's not quite going to work for this, but it's going to work if we modify it a little bit. For one thing, Dijkstra works on directed graphs. What we have here is an undirected graph, although we can convert it into a directed graph. The second thing is Dijkstra doesn't find all the shortest paths. It'll find a shortest path, but that's it. Meaning, you know, on something like this, if it starts out and it finds that the distance from 0 to 5 is 7, and then in the process of adding more nodes to the solution, it finds that, oh, you know what? We could go from 4 to 5. That's also 7. At that point, we don't care. Just it ignores that. Now, it does care about something like if it thinks the distance from 2 to 5 is 5, and it finds out, oh, you can actually go through 3 to 5, and the distance is only 4, it'll update that, but it just finds one shortest path. So we need to modify the algorithm to find multiple shortest paths. How are we going to do that? Let's see. Okay, so first let me call out some data structures here. Now you can do this without these extra data structures. I mean, our concern here is the way that these edges come in. Okay, you can't really access those in any kind of, you know, meaningful way, like what nodes are adjacent to node 1, right? Now, if you have an array that looks like this, you would have to go through it and say, oh, here's one here. This goes from 5 to 1, and here's one here. This one goes from 1 to 4. It isn't going to work. What you need is an adjacency list. Now, you can create an adjacency list just in the main method here. You know, under interview pressure, maybe that's easier. I like to you know, create and use objects when appropriate. So one thing that we have here is an edge-weighted graph. That's pretty simple. It's really just wrapping our adjacency list. So edge-weighted graph, constructor. It takes the number of vertices as a constructor. It stores that. It creates this adjacency list, and then it's a list. So it's a list of lists. I'm sorry. Yes, it is a list of lists. Okay, and then here's our adjacency list. We have an add edge method that it adds directed edges. It adds directed edges to the graph, and there's a ADJ method to return the adjacency list for any given vertex. So if we pass in there you know, vertex 1, it'll return this edge to 5 and this edge to 4. We have a data structure for an edge. Again, it's pretty simple. The constructors are the start node, the end node, and the weight. We put those into private variables. We have methods that we can call to get either in this case is going to, yeah, I may have overcomplicated this. I overgeneralized this a little bit, but either will return the start node, other will return the end node, weight will return the weight, and this is a requirement of Dijkstra's algorithm that we need these in descending order of weight. That is, we always we start with the start node, and then we add nodes in increasing order of distance from the source. So we want to get the smallest weight first. All right. Is there anything else in here? Oh yeah, pair. Again, this is part of Dijkstra's algorithm where we queue pairs of node and time, which is the node, and then let's say that the time that it takes to get from the source to that node. All right. So create the graph. Put all the edges in the adjacency list. Dist2. All right. I need to start writing some stuff here. Dist2. Dist2 is part of Dijkstra. All right, so let's put it here. Let's say D, and the length of that is going to be V. Actually, you know what? I don't want to do that one. It's going to take too long. Let's do this one. And actually, let's put it down here. So this will be D. D. Come on. Okay, take that off. Put this back on. You know what? I don't want to do it there. I'm going to do it right here. Do D. The length will be 4. 2, 3. Oh, why it keeps doing that? 4. What is the other one? Ways. Ways is something that we're adding. Dijkstra doesn't have that. We're keeping track of the number of ways of getting from the source to each vertex. All right. Let's see. Dist2. So we initialize Dist2 with big numbers. Okay. Because we're going to be making comparisons here. Like, have we found a shorter distance? So we want the initial distance in there to be very big so that the first distance that we find is guaranteed to go into the dist array. Ways. Ways, because an int array will be initialized with zeros. Right? Dist2. The distance to node 0 from the source, which is 0, is 0. Okay. The number of ways we can reach the source vertex is 1. All right. And then priority queue. Queue, the only node distance pair that we have at this time, which is node 0, distance 0. All right. While, oh, wait a minute. No, I think I can scroll this. All right. Yeah. The while loop is really the crux of the rest of the argument. All right, pair. So we're going to poll the current pair, and that is this right here. Current node is 0. Current time is 0. Is 0 greater than distance to 0? And actually, it's the same. All right. So we'll continue, and for each edge adjacent to 0, we're going to find all of the neighbors of 0. So let's say we find 1 is a neighbor. So W will be 1, weight will be 2. If distance to distance to 0 plus weight, so that would be 2. If it's less than the distance to 1, and right now distance is initialized to large numbers, so it is less. So we're going to say, all right, distance to 1 is 2. Distance to, okay, and ways equals, ways at 1 is equal to ways at 0, meaning we now know of one way to get to node 1, and we will put this in the queue that is the node and the distance, which is 1 and 2. right? And well, actually, we've taken this out. We've pulled this, but we have to continue. There is one more neighbor of 0, and that is 3. So we'll go through this. W is 3, weight is 5. If the distance of 0 plus 5 is less than a very big number here, then we're going to set it to that distance. It is 5. Ways of getting to 3 equals ways of getting to 0. So that is 1. We know one way to get to node 3. And we'll put that pair in the queue. And that pair is 3, 5. Okay, 3, 5. All right, now we add these to the solution tree in increasing order of distance. So that's something that gets pulled off of here is this 1, 2. So U is 1, D is 2. Is 2 greater than distance to 1? And it isn't. It's the same. So for neighbors, let's use 3. W will be 3, weight will be 3 if the distance to 0, no. If the distance to 1, which is 2, plus the weight, which is 3. So if 5 is less than distance to 3, which is already 5, right here, it's not, it's equal. Now, this is new. This is not part of Dijkstra. Okay, Dijkstra at this point would just say, it's the same, I don't care. You know, I already have a path from the source to vertex 3 of length 5. So the fact that I found another one is of no interest. But for us, it's interesting. Because if the distance to 1, which is 2, plus the weight, which is 3, 5 equals 5, then we take ways at 5 and add ways at 1. So ways at 1 is 1, ways at 5 is 1, and we add that. And now we have, that's a little bit awkward. You know what? So that doesn't look like a big mess. Let's make that a 2. All right. Now from here, we would proceed to go from 1 to 2, and then we would process the neighbors of 2 and so on. That isn't actually going to get any bigger, though. It isn't going to help us to go through the 2 and the 3. So I shortchanged this a little bit because, you know, if you took an algorithms class, you'd probably spend a class period on Dijkstra's algorithm, and you know, I don't want to do that. So what I'm going to say is that it is Dijkstra's algorithm. We're modifying it somewhat to be able to use it on an undirected graph, and we're also modifying it to keep track of duplicate paths. Rather than just ignoring duplicate shortest paths, we're going to keep track of duplicate shortest paths. Otherwise, it's Dijkstra's algorithm. If you think that you may wind up in an interview talking about graphs and or Dijkstra's algorithm, then I'd encourage you to do a little research on it. It's not a difficult algorithm. It's kind of a breadth first search where there's a process of what we call relaxing an edge. So if we have an edge, for example, from vertex V to vertex W, and we relax that edge, what it means is that we test whether the best known way to go from the source to W is to go from the source to V and then take the edge from V to W. And if it is, then we update our data structures. All right, let's run this. Take that off and submit. Okay. I hope you will like the video. I mean, you know, there's nothing not to like about Dijkstra's algorithm. It's a nice algorithm. You should take a look at it in a little more detail. It's very nice and not it's nice and it's intuitive, I think is what I'm trying to say. And you can subscribe to the channel, subscribe to notifications, and that's it. We'll see you next time.